Alright, so for today's pre-lecture video, I thought it would be a good idea to give you a quick review of the cross product since it's used in calculating forces and magnetic fields a lot. So just to remind you, when we talk about the cross product, it looks, this is the symbolism that we use. This would be the cross product of A and B, and so the name comes from the symbol. It goes in the middle, the cross, and it's something that we encountered in General Physics 1, like when we calculated torque. It's also known as a vector product, and one of the reasons that's true is because the result of the cross product is a vector. One of the things that we also learned about the cross product when we studied it last semester is that it's not commutative. What that means is that if you switch the order of the vectors, you don't get the same answer. It actually is true that your answer is the negative when you switch it. And the last thing, well, not the last thing, but one of the other things that we want to remember is when you take the cross product of two vectors, those two vectors can always define a plane. So you can always put two vectors, you can always draw two vectors on a piece of paper. That's how you can remember it. And so they define a plane, and when you take the cross product of those two vectors, your answer is perpendicular to that plane. So the answer to a cross product is perpendicular to the two vectors that you used. Some other things that we might want to remember about the cross product is if you take two parallel vectors, or if they're in opposite or anti-parallel, the cross product is 0. And finally, that the direction of the right hand of the cross product, the result of the cross product, can be found using what we call the right hand rule. So let's just look and review the right hand rule. There's actually more than one way to do this, and so I've showed two pictures here. The one that I prefer is when you take your fingers in the direction of your first vector and you curl your fingers in the direction of the second vector. It just so happens your fingers only curl one way, and so you have to manipulate your hand to make it happen sometimes. But then if you take your thumb and you stick it out like you're hitchhiking, that is the direction of the cross product. Again, notice that if we had to do it backwards, you would get the negative direction. This right here is another method that you can use for the right hand to figure out the direction of a cross product. I recommend that you use the one that you can remember. I think that's the best approach. I like the first one because that's the one that I learned, and that's the easiest one for me. So when we're talking about how big the cross product is, so the right hand rule that we just looked at tells us the direction of the vector. How big the vector is of course the magnitude. So in this chapter, we're going to be finding the force on a moving charge in a magnetic field. And we find that the direction of the force is given by this expression. According to our rules for the cross product, the magnitude of this answer would be given by the magnitude of the two vectors times the sine of the angle between them. And so that's how we will find. These, of course, remember, these two terms are magnitudes. That means that the force is 0 if your angle is 0 or 180. That's if the two vectors, velocity and magnetic field, are parallel or anti-parallel. And we could also say that this would have a maximum value if your angle between your velocity and your magnetic field is 90 degrees. But in general, this is how we would find the magnitude of that force. It also helps us, we can make it more general, and it would find the magnitude of the cross product. And finally, another thing that I want to remind you of is how do we deal with a cross product if we have unit vectors? Because the previous expression that we used really only works when we know the magnitude of the two vectors and the angle between them. So what if I'm given our vectors in unit vector form? So I've just come up with two vectors, A and B, and I want to find A cross B. A method we can use is by creating a 3 by 3 matrix, and finding the determinant of this 3 by 3 matrix will give us our answer. So the top row is our unit vectors I, j, and k. Then in the second row is the elements of my first vector given in x, y, z order. And then the last row is my second vector. It's important that you do this in the right order because, as you remember, the cross product is not commutative. Now, we can do we could find the determinant by, doing these 3 by 3 multiplications, but it's easiest if we expand about a row. So when we expand about a row, we eliminate the row and column, the row and the column and the row that unit vector is in. And so for the 2 by 2 matrix that accompanies I, we have 2, minus 5, and minus 6, and 10. Then we have a negative j. It's a little math detail, but just remember there's a negative sign in front of the j. The 2 by 2 matrix we get by eliminating the top row and the middle column is 3, minus 5, and 4, and 10. And then finally, we have k, and we eliminate that row and column, and we get 3, and 2, and 4, and minus 6. Now what we need to do is we need to find the determinant of each of these 2 by 2 matrix, which is found by you multiply these two numbers together, and then you subtract the product of these two numbers. So let's go on to the next page and do that. So A cross B, let's just rewrite our matrices so we remember what they look like. And then when we do our multiplication to find the determinant, and if we simplify, we get 20 minus 30, j, you get 30, minus a minus 20, so it's plus 20, and then k is minus 18 minus 8, and so finally if we add the terms together, we get minus 10 minus j times 50 plus k times minus 26. Or it might look better if we write it like this, minus 10i minus 50j minus 26k. And this, of course, we can find the magnitude by using an extended Pythagorean theorem, and then the direction is given, and it's in the 3x, y, and z direction. All right, so that's our review of the cross product.